Okay, so welcome to the talk. So I'm presenting our paper on ITCS, whose title is A New Conjecture on Hardness of two CSPs with Implications to the Densest K subgraph and Other Graph Problems. I'm Zihan from Rutgers University, and this is based on joint work with Chuzhoy from TTIC, Mina Dalirrooyfard from MIT, and Vadim Grinberg from Weizmann Institute of Science. Okay. So in fact, the statements of the main results in our paper are somewhat long and hard to memorize. So a very high level takeaway is that we proposed a conjecture on two CSPs that can be seen as occupying a middle ground between the previous conjecture on two CSPs. And it also implies a hardness of approximation results of the densest K subgraph problem that also lies in the middle ground hardness of result in previous works. Okay. And our conjecture also implies connecting the hardness of some other graph problems. Okay, so that's a very high-level message. So what is this densest K subgraph problem, short as DKS problem? The input is a graph, which is a set of vertices and set of edges connecting them, and also an integer K. Okay, so for example, this is the input graph, and K is 10. Okay, and the goal is compute a subset of vertices that contains exactly K of the vertices in the graph, while the number of edges between these K vertices are maximized. Okay, so for example, in this instance, the input graph is on the left and the input integer K is 10, and the optimal solution is what lies within this orange circle. Okay, so orange circle contains 10 vertices, and the optimal solution cost is 19. Meaning that there are a total of 19 edges connecting them. Okay, so densest K subgraph is sort of one of the most basic graph optimization problems that has been studied extensively. Okay, however, despite all this extensive work, the understanding of its approximability is still quite incomplete. Okay, so to date, the best current approximation algorithm, due to Bhaskara in 2010, only achieves a n to the 0.25 plus epsilon approximation in n to the 0.1 of epsilon time. Okay, so this is best approximation result. And the best hardness of approximation proof is also very elusive, and the most previous result depends on various complexity conjectures. For example, Fage in 2012 shows that we cannot get a 1 plus epsilon approximation if refuting random 3 set is inefficient. Okay, and subset code in 2002 shows that we cannot get 1 plus epsilon approximation if the class NP does not belong to the intersection of all these D-time classes. Okay, and some stronger hardness result due to Rakhendra in 2010, they show that a super constant hardness of approximation can be proved, assuming the famous small set expansion conjecture. Okay, and Alone et al. In 2010 shows that also a super constant hardness of approximation proof if refuting random now Kn formulas is inefficient. Okay, and for some stronger conditional hardness conditioned on stronger complexity assumptions, Alone et al. In 2010 shows that 2 to the omega log n to the 2/3, like hardness of approximation, if the plantic clique problem is hard. Okay, and in the recent breakthrough by Manuransi in 2017, he showed that assuming the ETH conjecture, so exponential time hypothesis, then the problem is hard to approximate within factor n to the omega 1 over poly log n. Okay, so this almost a polynomial approximation, hardness of approximation. Okay, so our results also, our first main results also falls into this conditional hardness category. Okay, specifically, we propose a new conjecture on two CSPs and show that if the conjecture is true, then it is NP hard to approximate the DKS problem to within factor to the log into the epsilon for some small constant epsilon. Okay, so this factor is essentially n to the 1. So it is smaller than any polynomial, but it's larger than any polylog n. Okay, so our hardness result can be seen as occupying a middle ground between the previous super constant bounds and near optimal, near polynomial bounds. Okay, so it is middle ground conjecture. So our second group of results shows the approximation equivalence between the problem DKS and some other graph problems. There are maximum bounded crossing subgraph, dense K coloring, and RH graph coloring. Okay, so let's look at each of these problems separately. So in the dense K coloring problem, the input is a graph and an integer K. And the goal is to partition the vertices of the input graph into roughly n over k groups of size k each. Okay, and the goal is to maximize the number of edges with both endpoints lying in the same group. Okay, so that's similar to the densest k subgraph problem in the sense that in the densest k subgraph, the goal is to compute a single dense subgraph of G containing k vertices. And in the dense K coloring problem, we need the partition G into many dense subgraphs, each containing at most K vertices, okay, exactly K vertices each. Okay, so the second problem is RH graph coloring. Okay, so the goal is the input is a graph G and integers R and H, and the goal is to compute R vertex disjoint subgraphs H1 to HR of G, maximizing the sum of the number of edges in it truncated at H. Okay, so this problem is also similar to the DKS problem, as it is due in the spirit of computing many vertex disjoint dense subgraphs of a given subgraph. Okay, so the last one is called maximum bounded crossing subgraph. Okay, the input is a graph G and an integer L, and the goal is to compute a subgraph H of G with the crossing number of the subgraph being smaller than L. Okay, while maximizing the number of edges in the subgraph that we compute. Okay, so it is actually a variant of the famous crossing number problem whose approximability remains wide open until recently. There's a subpolynomial factor approximation on bounded degree graphs. Okay, that is irrelevant, but it is just to say that this is a variant of the famous crossing number problem. Okay, so this very last problem, maximum bounded crossing subgraph, it looks like irrelevant to the DKS problem on the surface, but in fact, they are all closely related to another central problems in routing called the no disjoint path problem. Okay, so specifically, they are all mentioned in the recent work by Chuzhoy, Kim, and Mina in 2021 stock, which shows that almost polynomial hardness of approximation result for NDP, assuming some conjecture. Okay, so it is actually a conditional hardness result. Okay, so in particular, their work shows that no disjoint path problem is at least as hard as the RH graph coloring problem. Okay, and they originally wanted to prove that the RH coloring problem is hard, but they did not manage to do it. And in fact, they only managed to show a conditional hardness result for a specific variant of the RH graph coloring problem, which is still fortunately valid for a reduction to NDP. So they show a conditional hardness result for RH graph coloring, a variant of it, and then reduce NDP to it. That's how they prove the conditional almost polynomial hardness of results for no disjoint path problem. Okay, and our work shows a conditional hardness result for DKS, and DKS as it is equivalent in approximation to all these three problems: RH coloring, dense K coloring, and maximum bounded crossing subgraph. We also show directly a conditional hardness of approximation result on this RH graph coloring problem. So we sort of achieve their original goal. Okay, so this is the second group of result. It is showing that these problems are equivalence in the approximation. And we will not go into the details of these problems or how to prove the equivalence between them. But roughly speaking, the equivalence result shows that if one problem has a alpha n approximation, then the other problem, one of these three problems, has either a O alpha n approximation or O alpha n square or O alpha bracket is some quasi polynomial in n factor here. Okay, so these are not exact preserving the approximation, but roughly they are all the same. And when one has a 2 to the log n to the epsilon approximation as stated in the conjecture, then all other three have the same order of approximation algorithm. Okay, so this is the equivalence in approximation results. Okay, so in the remaining time, I will focus on the new conjecture and briefly show how it implies the hardness for the DKS problem. Okay. The conjecture is called D2D bipartite 2 CSP conjecture, okay, where CSP stands for the constraint satisfaction problem. Okay. So what is a bipartite CSP? Okay, so the input is two sets of variables, like denoted by big X and big Y, respectively, and a alphabet A, where the variables in X and Y takes values from. Okay, and there's a constraint. There's a set of constraints C. Okay, and the goal is to find assignment. Like for each variables in X and Y, we assign the value from A to it. Okay, and we want this assignment to satisfy as maximum number of as large number of constraints in C as possible. Okay, so maximizing the number of satisfied constraints satisfied by this single assignment. Okay, so specifically, the constraints can be organized into a graph called constraint graph. Okay, so each constraint like concerns one variable small x in X and one variable in Y. Okay, that's why it's called 2 CSPs. Every constraint concerns two variables. And why it's called bipartite, it is basically because the constraint graph can be organized into a bipartite graph, where the left vertices corresponds to the small like variables small x in big X, and vertices on the right corresponds to variables in Y. Okay, and there's an edge between the small x and small y, like if and only if there's a constraint in the constraint collection C that concerning this pair of variables. Okay, so now for each constraint, we also need to specify what it means for it to be satisfied. Okay, so this brings us to the assignment graph associated with this constraint. Okay, so recall we need to assign each variable in X and Y a value in the alphabet A. Okay, which is for now a set of colors here. Okay, the red, green, brown, purple, and yellow. Okay, so for a constraint C concerning variables small x and small y, the assignment graph contains two sets of nodes. Okay, the sets of nodes on the left and sets of nodes on the right. Okay, where a left-right node represent the assignment that the small variable x takes color red. Okay, and a right green node represents the assignment that the small y takes the color green. Okay, and an edge in the graph is basically a truth table for the constraint, meaning there's an edge between the left red and the right green, if and only if when the assignments assign small x to red and assign small y to green, this constraint is satisfied. Okay, so this is the definition of this bipartite 2 CSP and what it means to like the graph has a constraint graph and assignment graph for each constraint. Okay, so this is the definition of CSP, and typically for CSPs, we focus on the so-called gap problem. Okay, so we're given two constants, C and S, called completeness parameter and the soundness parameter, all both between 0 and 1. And we want to know that if at least C fraction of the constraints can be satisfied simultaneously by an assignment, or no more than S fraction of the constraints can be satisfied by any single assignment, if we are promised that one of these possibilities will happen. Okay, so this is called a gap CSP problem. Okay, and usually there are two parameters characterizing the feature of this CSP, which we call D and D prime. Okay, so typically in previous work, we say that a CSP is D to D prime, if and only if for each constraint in its assignment graph, degree of every left vertex are exactly D, and the degree of every right vertex are exactly D prime. Okay, so I want to remark that it is in most previous work, it is equal to D and equal to D prime degree as required. However, in our new conjecture to be presented later, we only require the degree to be less than D and less than D prime. And we also call it a D to D CSP. Okay, so the most famous setting is the unique game setting, which is essentially one-to-one games. Okay, So in other words, for every constraint, the assignment graph corresponding to this constraint is a perfect matching. Okay, and the famous unique game conjecture proposed by Code in 2012, it states that for all constant epsilon, there exists a alphabet size A, such that the 1 minus epsilon gap CSP problem is NP hard for unique games. Okay, so it's NP hard to detect whether an input in a game is like at least D satisfiable or at most S satisfiable for this 1 minus epsilon combination of CS values. Okay, and he also proposed a related D-to-1 conjecture, which said that for all epsilon D, there exists a alphabet size A such that the 1 epsilon gap CSP is NP hard for D-to-1 CSPs. Okay, now the completeness need to be perfect, this conjecture. So 1 epsilon instead of 1 minus epsilon. So our conjecture states that for all epsilon now smaller than 0.5, okay, and for there's this combination of parameters D and S, where D equals 2 to the log n to the epsilon, and S equals 2 to the minus log n to the 0.5 plus epsilon. Okay, so this combination of parameters, which are both n to the 1, okay, so subpolynomial, such that the gap CSP, okay, so this combination of gap CSP is NP hard for this D to D CSPs. Okay, so this is our conjecture, this parameter combination. So apart from this the different parameter combination, there are two other differences between our conjecture and the old ones. Okay, one, we do not need the completeness to be perfect or almost perfect. Okay, so originally there's 1 plus epsilon here, and 1 minus epsilon here, and 1 here, and we only require it to be 0.5. Okay, this is significantly lower. Okay, and second, we pose no restriction on the alphabet size A. Okay, so previously it says there exists alphabet size which may depend on epsilon. Okay, and there's an alphabet size may depends on epsilon and D, and we pose no constraints here. Okay, and part of it is because that our D, okay, is already depending on n, so it's 2 to log n to the epsilon. So as the size of the CSP is at most n, D is also like a function of n. A can be just at most bounded by n as well. So it cannot grow arbitrarily large compared with n and also compared with D. So that's sort of not necessarily being there. Okay, so this is our conjecture. And one remark about our conjecture is that it can also be viewed as occupying a middle ground between the D-to-1 conjecture by Code and the hardness of approximation proofs that can be achieved by standard techniques, like, for example, 3 CSPs and together with parallel repetition. Okay, so specifically, if we use the standard techniques like proving hardness, constant hardness result of CSPs via parallel repetition, we can prove some slightly weaker version of the D2D conjecture, which require a significantly bigger D here. Okay, and what we are conjecturing is sort of stronger than that. Okay, we require D to be this small factor, which is like now out of the scope of the power reached by the standard techniques. Okay, so in this sense, our conjecture is also a middle ground conjecture between D-to-1 conjecture and standard techniques. So at the very end, I would like to briefly sketch how to prove the connectional hardness result of the densest K subgraph problem. Basically, assuming the conjecture is true, we want to show that it is NP hard to approximate the DKS problem within factor 2 to the log n to the epsilon. Okay. And we are going to prove by contradiction. So we assume that there exists a 2 to the log n to the epsilon approximation algorithm for this densest K subgraph problem, which we denote by ALG in red. And we want to use this algorithm to prove the D2D game, or to solve the D2D game, certifying whether or not it is a yes instance or no. Okay, so largely satisfiable or very lightly satisfiable. Okay, how are we going to do it? Recall that a CSP contains a constraint graph, and for each constraint, an assignment graph. Okay, so we will first construct one global assignment graph as follows. Okay. So we replace each variable x in the constraint graph by an assignment gadget. Okay, for example, x is a variable on the left, so it is a variable in the big X set, And now we replace this node with a gadget, which contains basically one node representing each element in A. Okay, so if A is still a collection of colors, then it is just 5 colors in A within this gadget. Okay, and a small red node here still represents the assignment being assigning red to X. Okay, and still this meaning. Okay, and on top of that, we plant for each constraint its assignment graph just between the corresponding two gadgets. Okay, so basically we have a assignment graph here, and it is between two collection of A elements, and now we have it here, and we just plant the graph here. Okay, so we do the same for other constraints. Okay, and we call the resulting graph a global assignment graph. Okay, and what we do next is to basically apply this approximation algorithm ALG for density subgraph to this graph. Okay, the key intuition is that if the CSP is a yes instance, meaning that a large fraction of this constraint can be satisfiable by a single assignment, then there exists a dense x plus y sized subgraph corresponding to this good assignments in the most natural way. So for example, if in this assignment, X takes the color green, then we basically pick this vertex. Okay, and if the small y takes a value red, then we just pick this vertex, and we pick all the corresponding vertex. This gives us a X plus Y subset. Okay, and if there are many constraints that can be satisfied by this assignment, then like basically there are a lot of edges corresponding to this assignment's truth table edges. Okay, and this is sort of a dense graph for us. Okay, this is basically the intuition how the conjecture can be related to DKS problem. And due to the time limit, I'm not going to more details. The real algorithm is much more complicated than this framework has shown. For example, on the one hand, it will consider the possibility that how a cheating dense subgraph may look like. Okay, and we are in fact not constructing one graph and run the algorithm once, but we will constantly decompose the graph into smaller pieces and recursively run the approximation graph on each of them and then do something else. Okay, and also there are many pre-processing steps that are needed in each iteration. Okay, so it's a whole iterative algorithm. It's a code type reduction. So that's basically it. It's basically, hopefully it shows some intuition of how this D2D conjecture can imply the hardness of approximation result for DKS problem. And that's basically the end of the talk, and just a quick summary and future directions. We proposed a new middle ground D2D conjecture on two CSPs, which imply middle ground hardness of approximation result for density K subgraph problem. And both middle ground, and I mean n⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ conjecture, maybe just prove it. Maybe some techniques in the recent breakthrough that proves 2-2-2 conjecture may help in proving this conjecture. Okay, so that's all I want to say today, and thank you for your attention.